what we might do is define a new dimensionless set of displacements. That means that we will divide the two translations, U4 and U5, by a characteristic length here, L, and then the rotation, U6, is already non-dimensional. First thing we'll do is cancel out the complex exponential, and that's shown here. We knock out e to the omega t. Now we have dimensionless coordinates involved, and we ought to be able then likewise to convert the coefficients into a dimensionless form. That's done by arbitrarily choosing three dimensionless ratios. At this point, I'm not calling these Buckingham Pi terms because we're doing this more from an analytical approach. But here's one that has the mass and frequency in it, so this is basically your eigenvalue. Then there are these stiffness ratios over here. This one even is additive and has two stiffnesses entering. You can see that I'm using K0 as the reference stiffness in all three terms. So now in this pi notation, you have the characteristic equation for a non-trivial solution to be the determinant of this total operator. And there are, in fact, three dimensionless ratios involved in there. So at this point you would say, I ought to be able to solve for one of those variables, such as pi 1, in terms of the other two. And then the question is that logical or not? A formal way to discuss whether you have the proper number of non-dimensional terms is called Buckinghams Pi Theorem. And this will give you an idea of how many terms are required by the dimensions of the problem. Experimentalists often use this method, but it's also useful for theoreticians. One way to approach would be to approach it blindly if you knew nothing about the physics of beams and rods and point masses and so on. Then you might start out with raw variables shown here, all the variables that enter the problem, and you'd look at the dimensions involved. Now we know that with our gravitational system that we use force, length, and time, and those are the three independent mechanical dimensions. Had there been a mass term in here, we would, well, there is, in fact, I'll say it that way, there is a mass term, and you have to get rid of the dimension mass by using Newton's law and replace it with force times squared over length. And so now the question is, how many original raw variables did you have? Well, there were 10 such terms. How many independent dimensions were involved? And these were all mechanical dimensions. There were 3. That would leave you 7 terms, and that's a prediction of the Buckingham Pi theorem if you don't use some insight into the problem. We'll use some of our analytical knowledge that we've gotten in setting up the actual equations of motion to do this Buckingham Pi argument. We know that mass and frequency only occur in that combination. We know that the stiffness of the axial portion of the beam element only has this characteristic. The axial component of the rod has this set of terms acting together, and then the bending stiffness of the beam acts only with these terms. And when you look at that, you find that they're all force over length. Now, if you think of it in that way, the only independent dimension really is this ratio of F over L, and viewed in this new way, the Buckingham Pi theorem says you should have 5 terms less this one-dimensional ratio that's appearing. You should have 4 independent terms remaining. What the Buckingham Pi analysis can't anticipate, however, is the additive nature of a couple of these stiffnesses and how the horizontal stiffnesses tend to add together. So although we've accounted for the way that the variables multiply together in clusters, we haven't accounted yet for the way that the stiffnesses that they sum and appear in sums. That's pretty hard to get out of a Buckingham Pi analysis. Now I'm going to use some trickery, and there's not much generality in this. I'm going to now account for the summation property of the variables in the horizontal and vertical dimension by adding up the stiffnesses in those two directions and claiming then you only have one stiffness horizontal and one vertical. When you do that, the Buckingham Pi theory would say that you only had two independent variables, and in this case then you could solve for one in terms of the other. Now, when we go back to the dimensional form of our equation, though, we still have apparently more than that. But what I'm going to do is use what's called static condensation, which we'll talk about later. And what that means is that you solve for the rotation u6 in terms of the other variables and eliminate it. We're going to get into that more seriously later on, but it gives a ratio as shown here and effectively eliminates one of the variables. So we'll use that static exact relation to reduce the problem a little further, getting rid of the rotation u6. There was no mass term associated with u6, and so it was relatively easy to uncouple. Then at this point, if we assume harmonic motion and non-dimensionalize, this intermediate equation here turns into this one, and now we're starting to get some real clustering of terms, and notice you've got this quantity out front appearing in the eigenvalue location. You've got this quantity appearing over here as a stiffness term. We've fortunately arrived at a mass matrix which is a unit diagonal matrix, and this is more simplification than we could have hoped for, and certainly goes beyond the Buckingham Pi theorem. It turns out we have two equations that only involve two non-dimensional ratios. And furthermore, those equations uncouple. So we get the chance again to solve for the eigenpairs for the first frequency and the second frequency. And when we do that, we find that omega 1 is this ratio of the K1 stiffness plus the linear spring stiffness K over the mass. If you think about that, that is a pure axial motion of the cantilever beam with the spring opposing the horizontal motion. So it's a rather pure mode that we might have guessed if we knew that the rod didn't couple into that. The second motion is actually the vertical motion, which adds the stiffness in bending, kind of a shearing force developed at the tip of the beam by the beam and the motion of the mass, and then the rod acting to prevent the motion. So again, you have the ratio of a sum of some stiffnesses over the mass. And those are the two frequencies. Now, someone who was really physically intuitive might have looked at this system at the outset and have seen that those two motions were so different that they would uncouple. But that's not clear. You really, I wouldn't have hoped that anyone in the viewing audience would have come up with this simplified uncoupled solution intuitively. Sometimes in an exam, though, we find people in a desperation will make such an approximation, and it turns out to be almost a stroke of genius, and I always appreciate that. That happens often, that people, when they're in a bind, will suddenly cut through all the nonsense and make a strong physical approximation. And as long as it doesn't throw the baby out with the wash, I usually appreciate that. Well, that's the end of this problem session.